Okay, I think we can probably go ahead and get started at this point. We may have a couple more people joining, but we should go ahead and start. So I think Xiaolong is going to do the introduction, so I'll let you do that, Xiaolong.
Yeah, so thanks for everyone for coming. So it's my pleasure to introduce Salome. So our speaker today. So Salome is a PhD student at Göttingen University and Yale State University. So she works on simulation of cosmological simulations with magnetic field. So she is particularly interested in the evolution of the primordial magnetic field in cosmological simulations. Today she will give us a talk about her recent work on the evolution of primordial magnetic field through large-scale structure.
Thank you. Thanks. Yes, so I will start then now. I hope. Oh, 1 second. Yes. Hello, everyone. Thank you for inviting me and for giving me this opportunity to talk to you about evolution of primordial magnetic fields during large-scale structure formation. Oh, somehow I cannot. Okay, yes. First, I start by asking what are primordial magnetic fields and what we can learn from studying primordial magnetic fields. Primordial magnetic fields are magnetic fields originating in the early universe and then evolving with our expanding universe during different phases of its cosmic evolution. There are several high-stakes reasons for studying primordial magnetic fields, including their effect on cosmic microwave background, on light element abundances during Big Bang nucleosynthesis, or on the reionization history of the universe. Since primordial magnetic fields induce additional density perturbations in the early universe, they can affect the angular power spectrum of CMB temperature towards small scales. And since primordial magnetic fields can dissipate their energy into intergalactic medium, they can raise the intergalactic medium temperature and alter the reionization history of the universe. So therefore, primordial magnetic fields can give us a hint on some of the new physics of the early universe and may help us in resolving the tangents of standard cosmology. Apart from signatures, the physics of primordial magnetic fields include their generation and evolution. And in this talk, we briefly review their generation scenarios and evolution during early universe. And we focus on their evolution during structure formation, which is what we do in our work. In particular, in our research project, we ask a question: when looking at the magnetized cosmic web, can we distinguish between different primordial magnetogenesis scenarios? So I will finish talk by discussing the observational perspective of our work. One naturally asks where the hypothesis of primordial magnetic fields come from. And observations show that not only planets and stars, but also galaxy and galaxy clusters are permeated by magnetic fields, the strands of which are of the order of microGauss on galaxy and galaxy cluster scales, and they are correlated at least on kiloparsec scales. Recent observations have even detected the magnetization of so-called bridges scales. And here I show the figure from these observations of two merging galaxy clusters. Pink color show the emitted thermal emission, and blue color show the radio emission visible through synchrotron emission, which itself traces the magnetic fields. And as we see here, we observe this emission not only on the scales of galaxy clusters, but also in the intercluster medium. And moreover, recent observations of blazar spectra have shown to be compatible with non-zero magnetic fields in cosmic voids. And these observations put a lower bound of the order of 10 to the minus 15 Gauss on the magnetic field strands in cosmic voids. In this sketch, I showed the trajectories of the high energy gamma rays emitted from blazars. So tera-electron volt energy gamma rays are emitted from blazars, which then interact with extragalactic background light, producing electron-positron pairs. And then these electron-positron pairs are upscattered with cosmic microwave background photons via inverse Compton scattering, producing secondary giga-electron-volt emission. Given the distance scales involved in this type of study, it's probable that these electron-positron pairs are produced in cosmic voids. And then if magnetic fields in cosmic voids, they can deviate these electron-positron pairs and suppress the secondary giga-electron-volt emission from our telescopes. So this type of observations this type of observations make us think that this observed magnetization of the universe as a relic magnetization, and motivates us to study the primordial magnetogenesis scenarios. If the observed magnetic fields are indeed of a primordial origin, then how they could be generated. And if we look at the induction equation, at the evolution equation of magnetic fields, the first term, where V is velocity and V is a magnetic field, is responsible for the growth of magnetic fields, while the second term, with sigma being the conductivity of the fluid, is responsible for the diffusion of magnetic fields. So this equation implies that in the high conductivity limit, magnetic fields are just decaying with the expansion of the universe, here A being the scale factor. And what it also implies is that if magnetic fields are zero at initial time, then they would be zero at any later time. Therefore, one requires existence of very weak initial weak-set fields, which then would grow and would be amplified on the scales of galaxy clusters to the order of microGauss strands. So the competing scenario for the primordial magnetogenesis is an astrophysical scenario which generates these seed fields in the late universe before structure formation or during structure formation. And in this case, additional term is added in the induction equation, proportional to the gradients of electron number, density, and temperature. And if there be a non-parallel density and temperature gradient in the charge-neutral universe, then these weak-set fields could be generated. Although this mechanism generates magnetic fields locally and then needs transfer of magnetic energy into larger scales to reach the large coherence scales on, for example, on galaxy cluster scales. On the other hand, in the primordial scenario, magnetic fields could be generated during inflation or during phase transitions. In the inflationary scenario, primordial magnetic fields would be the correlation lengths of these primordial thermal invariance of electromagnetic action in order magnetic fields not to decay during the accelerated expansion of the universe. And usually in this case, one considered the coupling of electromagnetic action with scalar fields, such as, for example, inflaton. In the phase transitional scenario, magnetic fields could be generated during electroweak or quiescent phase transitions. And in this case, their correlation lengths would be bounded by the Hubble horizon scale at the moment of generation. And during this epoch, the seed fields could be generated through this, during the explosion and collision of the bubbles of different phases. In our work, we study both inflation and phase transition generated primordial magnetic fields, and we evolved these magnetic fields from redshift 50 with our cosmological MHD code ENZO. We employ long-decidium cosmology without cooling and feedback physics in order to solely focus on the amplification of magnetic fields during structure formation. And the novel approach of our work is that we take into account the evolution of magnetic fields in the early of these primordial magnetic fields in the early universe. So in particular, we take the results of the MHD simulations with the pencil code, and we take them as an initial conditions for our cosmological simulations. So we study primordial magnetic fields that can have different topologies. They can be either homogeneous uniform or statistically homogeneous. And in both cases, magnetic fields can be characterized by their energy spectrum, which is defined with this equation, where B is a normalization factor and B is a Fourier transform of the magnetic field, and K is a wave number. And in the homogeneous uniform case, magnetic field energy spectra is just Dirac delta function, which has a peak at K equals 0 wave number. And in this statistically homogeneous or stochastic case, magnetic energy spectra can be power law, or it can also be characterized by a peak in the spectrum. An example of homogeneous uniform magnetic field can be inflation generated primordial magnetic field, while stochastic fields can be generated from phase transitions. And knowing the magnetic energy spectra, we can also define the magnetic correlation lengths, which is the weighted, which is the inverse wave number weighted by the magnetic energy spectrum itself. In the case of statistically homogeneous magnetic field, they in addition can be characterized by helicity. Helicity can be interpreted as a measure of corkscrew-like motions in a magnetized fluid, and it's defined as a volume integral where A is a vector potential and B is a curl from the vector potential itself. And in this sketch, I show the cases when helicity is 0 and when it's not 0. In the left sketch, I show the magnetic field lines, which are not characterized any twist, writhe, or linkage, and therefore helicity is 0. And in the right, I show the linkage of magnetic field lines, and therefore helicity is not 0. In addition, helicity is a conserved quantity when in the highly conducting fluid. Evolution of primordial magnetic fields in the early universe is studied in the so-called magnetically dominated decaying MHD turbulence regime. And in this primordial magnets, assume that magnetic correlation length initially is of the order of phase transition bubble size. And then during its decaying turbulence regime, magnetic fields develop large coherent scales. It turns out that this result is helicity dependent. Or if we now talk in terms of the magnetic energy spectra, here I show the sketches for the magnetic energy spectra for both cases, for helical and non-helical models. Y-axis show magnetic energy spectra and x-axis show a wave number. Versus the magnetic energy spectra, and we see that in both cases, magnetic energy decays on large scale, on small scales, and it increases on large scales and develops a power law spectra towards large scales and turbulent spectra towards small scales. And also, as we can see in the helical magnetic field case, the height of the peak is not decreased during its evolution, which leads to the larger correlation lengths in the helical scenario. So this process, when the magnetic energy decays on large scales and it decreases on small scales and increases on large scales, is called inverse cascade. So the energy is transferred from small to large scales. In the case of inflation-generated primordial magnetic fields, in this case, magnetic fields can already have large coherent scales. And usually their spectra is assumed to be scale invariant. And during the MHD decay, they develop turbulent spectra. And in this case, this result is not helicity dependent. Now we turn our eye to the evolution of primordial magnetic fields during structure formation. And I show here our initial conditions for the MHD, cosmological MHD simulations and corresponding projection plots for the initial conditions. So here Y and X axis show coordinates, and color coding is according to magnetic field strengths. So in the we study inflation generated fields, which can be constant, uniform, as it is also depicted in this left panel. So magnetic field is just constant and it's directed along the diagonal, and it's characterized by direct delta function spectra peaked at k equals 0 wave number. And in the inflationary scale invariant case, we study the magnetic field, which develops turbulent spectra in the early universe. And in this case, magnetic field has stochastic distribution, and its amplitude is also varied. So in the phase transitional models, we study both helical and non-helical models. And as we could see, in this case, magnetic energy spectra is k to the first towards large scales and turbulence towards small scales. And in our case, we also take larger coherence scales for the helical scenario, as it's expected from the MHD studies. Although in our case, the coherent scales are larger than what is expected from these MHD simulations. And this is due to our limited resolution in our cosmological simulations. So here I showed the evolution of slices of the central slices of the magnetic field and their evolution from redshift 10, Y and X axis show coordinates, and color coding is according to magnetic field strengths. And so we see that when structure forms, magnetic field also grows, and it shows large coherent scales and more filamentary structure, large coherent scales on these filamentary structures in the inflation generated uniform and scale invariant cases. And if we look now at the final picture, indeed, we see that the larger amplitude are also observed for these seed fields, which have initially large coherent scales, while in the phase transitional models, we see more small substructure and also the lower amplitudes. Looking at the density distribution, here the light color show the higher densities, and dark color show cosmic waves and lower densities. We see that the different topologies of magnetic field does not affect the density distribution, and this is all actually expected, since magnetic fields have much lower energy compared to kinetic and thermal energies during gravitational instability. So in our work, we study not only different topologies of magnetic field, but also different initial strengths corresponding to 0.1, 0.5, 1 nanogauss mean magnetic field strengths. And here I show the normalized magnetic field and temperature versus overdensity profiles. So the different line styles show the different normalization, and the color coding is according to the cell mass falling into each bin. And we also show the tentative thresholds for the for different cosmic environments. And the black line here shows the expected adiabatic contraction scaling for the magnetic fields. Now, if we start from the massive objects, such as galaxy clusters, we see from the top panel that a magnetic field distribution differs according to the scenario. We see that the largest values of magnetic fields is expected from uniform and scale invariant models. And these differences between inflation and phase transition generated models decreases when we go towards smaller towards bridges and filament scales. And in the voice region, we see the opposite trends. Phase transitional models show larger magnetic field strengths. Now looking at the temperature distribution, we see that there is no difference in temperature in clusters, bridges, and filaments. But in the voice region, we see the dependence on the strength of the magnetic field and also on their topology. So we see that phase transitional models with larger initial normalization show the highest temperatures, and inflation-generated models show lower temperatures in this waste region. So we see that these environments are affected both by the initial topology and the initial strength of the magnetic field. As we mentioned in the beginning, primordial magnetic fields can affect the temperature evolution. And in this case, y-axis show temperature and x-axis show a redshift. And this red line is the expected trend of the temperature evolution if one does not take into account the existence of primordial magnetic fields. And the purple line showed the evolution of temperature when one takes into account the primordial magnetic field. And the solid lines is for the uniform model, and the dotted line is for the scale invariant model. So in our work, we also studied and compared the evolution of thermal, kinetic, and magnetic energies, which is shown in this figure. Y-axis show energies and x-axis show time. And in the secondary axis, we also show the redshift. So we see that the kinetic energy from our simulations does not show any dependence on magnetic field, as well as the thermal energy. Although we see, and as expected, inflationary models show larger magnetic fields at late redshift when comparing to phase transitional models, helical and non-helical models. Also, we see the opposite trend in the thermal energy at early redshifts, when inflation generated uniform and scale invariant models show lower thermal energies, and larger heating is expected from the non-helical and helical models. Now that we have seen the evolution of magnetic energy spectra in the early universe, we can look at the evolution of magnetic energy spectra during structure formation. And here I show the evolution of magnetic energy spectra for inflation-generated uniform and scale invariant models. Y-axis show magnetic energy spectra, and x-axis show wave number, and light color show evolution at early times, and dark color show evolution at late times. And so as we see, magnetic energy grows in both cases, and we see that the largest power is obtained on large scales. And we, in both cases, we see the similar evolution towards small scales. And contrary to what we could see in the evolution of magnetic energy spectra in the early universe, here we see the growth due to, we see the growth due to formation of massive structures. I forgot to mention that the K equals 1 here corresponds to 1 co-moving megaparsec scale, which is approximately scale of galaxy clusters in our simulations. So, and we see the growth due to formation of massive structures. And the differences between uniform and scale invariant models, where a uniform model show constantly, always growing magnetic energy, while in the scale invariant case, we see decay at initial times. So in the case of phase transition generated helical and non-helical cases, we see a different picture, and this evolution depends on the initial characteristic scale of the helical and non-helical models. So first we see that the growth is moderate on large scales. So this is similar to the trend of their evolution in the early universe, although this growth is moderate. during structure formation. And we see that the initial magnetic energy spectra on the peak scales decreases, and it's redistributed toward the formation of the massive structures. So we see an opposite trend. We see that the shift of the magnetic energy spectra is shifted from large to small scales, where we expect this massive formation of massive structures. Now, for more clarity, I showed the I compare in this figure magnetic energy spectra. Solid lines show the final magnetic energy spectra for inflation generated at phase transitional models, and dashed dotted line show the initial spectra for stochastic models. And in the secondary axis, we also show the corresponding linear mass scales to these frame numbers. So we clearly see that the differences between inflation generated and phase transitional models are significant on these largest scales, while these differences decreases when we go towards small scales. And how can we explain these differences? Now, looking at the induction equation, growth of magnetic field perturbations is depending on the growth of velocity perturbations and also on the initial magnetic field strengths. And since velocity perturbation itself depends on density perturbations, and we don't expect any imprint from primordial magnetogenesis on the velocity perturbations, then the differences which we see is coming from the initial magnetic field strengths. So in particular, in the helical and non-helical models, initially magnetic energy is so they are characterized by the initial characteristic peak, and most of the energy is contained on these scales. And therefore, on large scales, we obtain mean field strengths close to zero. While in the inflationary models, since in these models we have large coherent scales, their mean strength is not zero anymore, and therefore we obtain the large amplification on these large scales from these models. On small scales, on the other hand, from the magnetohydrodynamical simulations, we expect that it's expected that the imprint of the different primordial magnetogenesis is erased by the amplification of these magnetic fields by dynamo mechanism, which is a conversion of kinetic energy into magnetic energy, leading to exponential growth of magnetic fields. Although this is not really checked for this cluster on these galaxy cluster scales, and since in our simulations, these are the scales which are poorly resolved, in order to check the dependence on the initial topology of magnetic field, we need to simulate these scales with higher resolution, which is what we do in our current work. So these scales we need checked and in order to see the differences of primordial magnetic field, whether still whether they are not erased on these galaxy cluster scales. So we also studied the evolution of magnetic correlation lengths. Although the trend in the magnetic correlation length is also affected, can also be affected by the limited resolution on small scales. It's still interesting to see how the different, how the correlation lengths from different seed fields evolve during structure formation. Here, y-axis show magnetic correlation lengths and x-axis show time, and on the secondary axis, we also show redshift. So here are different paces in the evolution of correlation lengths. At first, we see the increasing trend in the magnetic correlation lengths. And so I forgot to mention, these gray lines here show the correlation lengths for the density field. And initially we see that the magnetic correlation lengths, as well as the correlation for the density field increases. which is due to the fact that initially we have large-scale modes grow faster than small-scale modes. And at later times, we see the decrease in magnetic correlation lengths, which is due to the formation of massive structures and that the growth of small-scale modes catch up the growth on large-scale modes. And at later times, at final redshifts, we see that in the stochastic models, correlation length decreases. And it's only the uniform case which shows the increasing trend, which also follows the evolution of density correlation lengths. And this is due to the fact that in this model, we have large initial correlation lengths. And in the stochastic models, we don't, so at final redshift, we have a damped growth of small scale modes, which is imprinted in the uniform case. Since it always shows growing modes on large scales, while in the stochastic models, we don't observe this amplification of large scales. Therefore, we observe the decreasing trend in all three scenarios. So finally, we observe at final redshift that the correlation lengths from inflationary models are larger than from phase transitional helical and non-helical models. In this last part, I will discuss observational perspective. So for this, I will introduce Faraday rotation effect. So this is an effect. So when polarized radio emission from distant sources is affected by an intervening magnetized plasma, which rotates the intrinsic polarization plane of a wave. And this change of the polarization plane is proportional to the so-called rotation measure and observed wavelengths squared. And rotation measure itself is an integrated quantity of electron number density and line of sight magnetic field strength. So when one discusses the sources being at extragalactic scales, then in this case, we should take into account the contribution in the rotation measure from all magnetized plasma along the line of sight. So the rotation measure will include contribution from the magnetized plasma being in or around the source, and also from the magnetized plasma in or around galaxy, and the magnetized and also contribution from this intervening intergalactic medium. But since we are interested in magnetic fields, in extragalactic magnetic fields, we wonder how we can constrain RM-IGM, which can help us in constraining primordial magnetogenesis. And in the recent works of Verstrom et al. And O'Sullivan et al., these authors presented a new approach, which is based on the rotation measure observations for physical pairs and for random pairs. So in this right sketch, physical pairs mean that these are double-lobed galaxies, and RM1 and RM2 are rotation measures observed from the two different lobes of the double-lobed galaxy. And in the left sketch, RM1 and RM2 are rotation measure observed for random pairs, which are galaxies being at different redshifts. And in this approach, the main point is that these authors calculated rotation measure difference RM1 in RM1 and RM2, difference in the RM1 and RM2 separately for physical and for random pairs. And because of this second intergalactic medium present in the case of the random pairs, one expects the extra contribution in this difference in delta RM RMS for the random pairs, which actually was also obtained from the observations. So in these observations with Loeffler and NVSS observations, they have shown that these random pairs random pairs show the excess rotation measure difference, which is caused due to this intergalactic medium, and this itself limits the inter-ARM-IGM contribution, and therefore limit the magnetic field strength in the cosmic voids or in the intergalactic medium, which is which should be the below 40 or 4 nanogauss according to the Loeffler and NVSS observations. So in our work, we also studied the rotation measure from our simulated cosmic web. And here I showed the rotation measure maps for different seeding models. Y and X axis show coordinates, and color coding is according to rotation measure values. So as we see in the inflation generated uniform and scale invariant cases, we see a larger coherent structures and larger amplitude of rotation measure when compared to phase transition helical and non-helical models. And this is the result of rotation measure being an integrated quantity. And because coherent fields give rise to larger and correlated signal, and because of the magnetization of larger magnetization level from inflation generated uniform and scale invariant models, we see the largest and correlated signal from these scenarios. So in our work to compare our rotation measure distribution with the mentioned works of Wernstrom and Sullivan et al., we have to stack cosmological boxes and produce light counts, and then measure the difference between random and physical pairs. Although in this current work, we defer this to our future work, this technique, and in this current work, we use a simplified approach. Instead, we take a warm hot intergalactic medium from our simulated data set from redshift 3 to redshift 0, and for each redshift snapshot, we calculate RM1 and RM2 according to the rotation measure distribution function. And then we calculate difference between this RM1 and RM2 for all possible combinations of these redshift pairs. So this procedure leads to difference between RM1 and RM2 for uniform scale invariant helical and non-helical models as listed here. And we see that the uniform and scale invariant models show largest values compared to helical and non-helical models. Although if we compare these obtained values with the corresponding values obtained from the observations, we see that they are lower than these values from the observations. So in our work, as we said, for comparison with this observational data, we needed to stack cosmological boxes, although these differences comes from the fact that in observations, one always has galactic contribution, which we also did not take into account in our work. Nevertheless, we can ask ourselves what are the magnetic field strengths from these different scenarios that would reach the that would give us the observed values of rotation measure in intergalactic medium, and this limits our magnetic field strength to be less than 3 nanogauss for the inflation generated magnetic fields and to be less than 6 nanogauss for the phase transition generated magnetic fields. So, and to sum up, we see from observations that primordial magnetic fields can be good candidates for the observed large-scale magnetization of the universe. And we studied the evolution of these primordial magnetic fields, of inflation and phase transition generated primordial magnetic fields. And we also take into account their evolution in the early universe. So, and our cosmological simulations have shown that the results are topology dependent. In particular, we could see that large-scale fields lead to largest magnetization level in filamentary structures. And we could see that contrary to the trends in the early universe, here magnetic energy grows and it shows buildup of the magnetic energy on the scales of collapsing objects. On the other hand, stochastic models may have a larger heating rate in the intergalactic medium and can affect the temperature evolution in the intergalactic medium. And also our rotation measure statistical analysis would favor inflation generated primordial magnetic field as they show the large coherent scale and largest rotation measure values on the largest scales of the universe, although we cannot exclude phase transition generated primordial magnetic fields. And meanwhile, future observations with a square kilometer array is promising for detecting, for giving us more precise rotation measure values on the scales of galaxy clusters. And in our ongoing work, we study the evolution of different primordial magnetic fields on the scales of galaxy clusters with higher resolution to detect and to check the primordial magnetogenesis scenarios on the scales of massive galaxy clusters. Thank you for listening.
Great, thank you very much, Salome. Really nice talk. We have plenty of time for questions. I will lead off because I had a couple questions. So one was actually related to the kind of last point you made there. And the power spectra that you showed, there was kind of a cutoff at around scales of a megaparsec. Is that physical or is that related to the resolution of the simulations that you have?
Do you mean, what exactly do you mean in cutoff?
So at like a wave number of around 1 here to larger wave numbers, there's a decline in the power spectrum. And it wasn't clear to me if that was just resolution dependent or if that was real physics there.
Yeah, so we think that these scales are mostly affected by resolution, and also that's why they also show the damped growth at final redshifts. And yeah, so this should be more resolution effects on these scales. Okay,
understood, yeah. And my other question was, so these simulations, you exclude cooling and feedback processes. Would you expect those to have any effect on the kind of larger scales that you're interested in here, or is it safe to ignore those?
I think on the on larger scales, I don't expect it will have an impact. Although on small scales, I think the trends in that case, magnetic field would can lead to larger growth rates, as is also seen in the other cosmological simulations.
Great, thank you. Let's see, Guillermo, you had a question? Guillermo, did you have a question you wanted to ask?
Yes, sorry. It's related to a similar question to the last question that Andrew asked, but so with no feedback and no cooling and at the resolution of simulations, you can form compact objects, right? Like supermassive black holes, for example. And in like radio galaxies, like when you see this, like, giant radio lobes, does that, imply that like compact objects like supermassive black holes in the center of galaxies, or maybe other sources of magnetic fields, can actually propagate, these very small scale magnetic fields out to megaparsec scales? I mean, I'm wondering whether there's some sort of like order of magnitude argument that can be used to say whether those processes are important or not on these large scales that you're analyzing.
Yeah, so the question is whether the more massive formation of more massive structures such as black holes can affect the evolution of magnetic fields on these very large scales. Right?
Yeah, the question is whether magnetic fields that are induced or produced or amplified at very, very small scales, like black holes or neutron stars, or sort of small scales like supermassive black holes in the centers of galaxies, whether they can actually propagate all the way up to these very large scales and affect the results like the things you're showing.
Yeah, that's a good question. Yeah. Example astrophysical scenario. Usually, when the evolution of magnetic field is astrophysical, then that can have large volume factors and can also transfer it into intergalactic medium. So for example, galactic winds and similar processes can transfer magnetic energy into larger scales. Yes, this is also a competing scenario of, and this is also sometimes said whether we can really detect primordial magnetic fields polluted also by the transferring of magnetic energy from this, for example, galactic winds, and it could be possible that this is already not already primordial magnetic fields in the cosmic voids.
See, thanks.
Do we have any other questions? Okay, I'm not seeing any. So in that case, let's thank Salome again for a really nice and interesting talk. And thank you everyone else for joining us.
Thank you.
Thank you everyone else for joining us.
Thanks.
Okay. Thanks very much. It was really good.
Thank you. Goodbye. Thanks.